Any discussion of the organic chemistry of carbohydrates necessarily involves a detailed look at stereochemistry. So in this lesson, I'm going to give you the ground rules as far as the stereochemistry of sugars. Okay, so for monosaccharides in the open chain form, an aldose with N carbons will have N-2 stereocenters, and a ketose with N carbons will have N-3 stereocenters. Okay, so let's look at some examples of this. So the simplest sugar is what we call glyceraldehyde. It's a 3-carbon sugar. And as you can see, indicated with a blue asterisk, it has 1 stereocenter. Glucose is a 6-carbon sugar, also an aldose, and it has 4 stereocenters. And then fructose is a ketose. It is a 6-carbon sugar, so therefore it has 3 stereocenters, and they're all indicated with blue asterisks. Okay, so recall that if a molecule has N stereocenters, there will be 2 to the N stereoisomers. So with 4 stereocenters in a 6-carbon aldose, there will be 16 possible stereoisomers. And here they are, the 16 aldohexoses. So these are drawn in what are called Fischer projections. We're going to look in more detail about what that means in the next lesson. But for the moment, just accept the fact that these are a common way in which we draw sugars in the open chain form. And you can see from the headings that I put on here that 8 of them are what we call D-aldohexoses, and 8 of them are what we call L-aldohexoses. And we will also discuss the meaning of D and L in a subsequent lesson after the next one. So what I have indicated in red here, D-glucose, D-mannose, and D-galactose, are the 3 most important sugars biologically. So what you should look at, if you look at the structure of D-glucose, its enantiomer is actually what we call L-glucose. And in order to get the enantiomer, as you remember when you have molecules with multiple stereocenters, you need to invert all of the stereocenters. And the way we invert stereocenters in this way of drawing molecules is you can see that some of the OHs are on the right and some of the OHs are on the left. So if you just flip all of them, you get to the enantiomer. So anything that starts out on the right goes to the left, and anything that starts out on the left goes to the right. So as you should remember from first semester's unit on stereochemistry, every compound can have only 1 enantiomer, which means that all of the rest of these stereoisomers are actually diastereomers of D-glucose. So it turns out that the ones on the top, the D sugars, are the naturally occurring sugars. And the L sugars tend not to be naturally occurring, but you can still make them in a laboratory and purchase them if you need to. And the way we refer to their relative stereochemistry is actually using common names. So the other 7 D sugars have different names, and all that they the only way they differ from glucose is the relative positions of whether the OHs are on the right-hand side or the left-hand side. So you have allose, altrose, mannose, gulose, idose, galactose, and talose. And these common names are, as we said, used rather than naming these completely systematically, which would have to make you calculate R and S at each of the 4 stereocenters. So you would have to say R, S, etc. Those would get long and kludgy really quickly. So as we said, glucose, mannose, and galactose are the most prevalent aldohexoses in nature. So what defines glucose is when you have the OH at C3 on the left side. Okay, so the carbons are numbered here with the aldehyde being C1. So C2, 3, 4, and 5 are the 4 stereocenters. So all of these other arrangements where you have something other than the OH at C3 on the left side and the rest on the right side requires a different name. And the other 4 structures that I have drawn on this slide, once again, next to glucose, have a special relationship with glucose in that they are the epimers of glucose. So epimers are defined as diastereomers that differ at only one stereocenter. So a molecule with 4 stereocenters will have 4 epimers. And the 4 epimers of D-glucose are D-mannose is the epimer at C2. Okay, so you can see there that C2 has the OH on the left side rather than the right side. D-allose is the epimer at C3, so that has the OH at C3 on the right side. D-galactose is the epimer at C4, so it has the OH at C4 on the left side. And then L-idose is the epimer at C5 with the OH at C5 on the left side. So if you were to look back at the previous slide and look at the difference between the D sugars and the L sugars, notice that all of the L sugars are epimers at C5 of a different D sugar. And we will come back and look at this a little bit more systematically when we define D and L in 2 lessons. But before we get to that, what I want to do in the next lesson is go over what is this thing called a Fischer projection and how do we get to it and what does it mean as far as conveying 3-dimensional stereochemical information.